thank you for coming. This is Astronomy 5. Now, where's the number? There it is. Okay.
No, I'm gonna have to hold that a minute.
Did it work? It froze again.
Now you can start.
Yeah.
That will work there.
Yes.
Okay.
The previous talks were it was a humorous talk on mathematics and astronomy. I tried to make it humorous. It's difficult with mathematics, but I also talked about the history and of astronomy and about the moon and the planets. Also, another person did talk on comets and asteroids, but this will be the 5th one. Okay, right there. Okay, now have any of you seen the Grand Canyon? All right, it is just awesome. And here is a photograph of Jupiter and the 4 of its moons. Have you seen this in the telescope? It is amazing just to look at that. And here is Saturn, a photograph of Saturn that you can see through a telescope. Okay, now this, I think, is things like that are awesome. You look at them in awe, okay, and you don't think about your problems or the problems of the world. You're just thinking about those things that you're looking at. And I hope now that my talk will be such that you will think that it is awesome. A man has written a book, and the name of it is Awe. And he tells about these type of things. And I think it'd be worthwhile to get that book and read that. Okay, today I want to talk about the solar system and the stars a bit. Now, right here is the planet. Up in here are the planets, and they're all drawn to scale. The size of them are drawn to scale. Okay, the Jupiter and Saturn, and right there, if you can see it, is the Earth. And right there is Mars and Venus and Mercury, and over here is Uranus and Neptune. And I saw this photograph and I thought, gosh, I wonder how big the sun is in comparison. You know, because these are all drawn to the size of them, to the scale. Well, I did a little bit of mathematical computation, and I came out with this. is how big the sun is with respect to the planets. It's amazing. Now, if you took the Earth away from here, how far away would you have to get to be in the same scale? Well, it turns out to be a little bit more than a football field away. The Earth would have to be that far away. So you can imagine, compared to here, the Earth is over there, it'd be just a speck. Okay, so that's a little bit of an idea of the size of the planets. Now, here is a drawing or a chart of the planets. And it's, if you notice up in here, it is the 14th. Oh, by the way, today is Pi Day. Did everyone know that? It's 3.14.
Oh, it's today.
March the 14th, 314. It's Pi Day.
Yeah, today's not the 14th though. It's not 14th.
Oh,
It's like Tuesday.
oh, a few more
That's
days.
Tuesday.
Okay, anyway, there is the sun is here and the Earth is there and it goes around like that. And Venus is there and it goes around like that. And Mercury around here and Mars around here. And you see Mars is over here, Jupiter and Mercury, and the Earth is right here. So what I wanted to do with this is that if the sun is right in this direction, here we are on Cape Cod, right here, okay? And if the sun is directly ahead, now as we rotate from noontime, come around like this, pretty soon the sun is set. But up in there, you can still see Venus. And that's how you can, up in here, the sun is just set, and now you can see Venus over here. Now, Mercury you can't see because it's sort of behind the sun. And but Mars is right up ahead, right up above, right now. Okay, so oh, next one. Oh, what did I do? Oh, what happened?
Want to go
Am
back?
I getting the wrong one?
Yeah, go back.
It won't go back.
Sometimes it was sticky. Oh, it's stuck. Go. Oh, here.
Did you get it to go back?
Which way?
I want to go back.
I didn't know which way you would turn.
It wasn't going back.
This going back?
Yeah, right there. That's where I want it. This, now, notice, If the sun is there, now the earth is way in here. And Mars and Jupiter, but out here is Jupiter and Saturn. And that's where they are right now, today. And the earth being right here, if you look up that way, notice that right on that line, they're almost the two of them. If you go out there and look at Jupiter, you'll see see Venus, you will see Jupiter also, the two of them out there, almost in the same line. So, but Saturn, if you get up early in the morning, just before the sun comes up, you might be able to see Saturn. Okay, I hit this one. No, it doesn't move. Why doesn't it move? Am I hitting the wrong?
No, Lisa said that.
There. I guess I'm not hitting it in the middle or something.
Okay.
Anyway, you know, their Earth is about 93 million miles from the sun. 93 million. And from your high school mathematics, the circumference is equal to 2 pi r, r being the radius, or 93 million miles. So the circumference is r times 2 pi, and it turns out to be 584 million miles that we travel around the sun each year. That many million miles. And the distance in one day is 1.6 million miles. 1.6 million. Oh, well, how about per hour? It's 66,000 miles per hour. That's about 100 times faster than an airplane goes. 100 times faster. Every minute we are moving with the earth around the sun 100 times faster than an airplane goes. That, to me, that's awesome. And we don't even know it. We don't feel it. It's like being in an airplane. You're sitting in there and it's going 600 miles an hour, and you don't even know it unless you look out the window. You're not moving. It's the same way. The earth is moving that fast and we're going with it. Same way. Oh, the speed of light. I don't know if all of you know that light travels at 186,000 miles per second. They figured this out. No? Here. Oh, I jumped one. It goes the wrong way.
It jumped a couple of them. Just go back.
There, if you're getting there. Well,
Is that what I? No.
look at the screen. It seems like you're going forward. I think maybe you could go over and help them, and then you can just tell you.
there.
It's very sensitive, I think.
Oh, what happened?
Go back once.
No, it goes there. Okay. Light travels from the earth to the moon. To the moon now in 1.5 seconds. You know, our spaceships take a couple of days to get there, but the light goes in 1.5 seconds. Now, when I was working, which is many years ago now, we were wondering how to control a vehicle on the moon by here on Earth. We would say steer it and look at what was going on in the television from the moon, but it took a second and a half for what was going on the moon to get here. And then if we did something, it'd be another second and a half before it did it. So there's a delay of 3 seconds. So 1001, 1002, 1003. That's quite a delay. If you were to drive a car and around and have a 3 second delay, you would be in an accident pretty quick. So anyway, we were wondering how slow we would have to drive to control a vehicle on the moon. I think I just have to tap it.
Yeah, just one.
So now, if the sun is 93 million miles from us, and so if you figured it out, it'll take 8.3 minutes for light from the sun to get here. 8.3 minutes. It's quite a delay, but we're a long ways away from, 93 million miles. Well, okay. Here is the Earth is a sphere, and to locate some place on the Earth, use latitude and longitude. Probably all of you know that. The latitude is the number of degrees up from the equator, and the longitude is measured from Greenwich, England, which is right near London, and you measure going east or west. So many degrees, and so Cape Cod now has a latitude and a longitude. And every other point on the Earth it can be designated by its latitude and longitude. Okay, now, in a similar way, there is a celestial sphere. Now, think about out there, the stars out around us, all around us. Completely. It is not a physical sphere, but it is a virtual sphere out there of all of the stars, the sky, all around us. And rather than having latitude and longitude, the astronomers have come up with declination and right ascension. And I'm not going to go into that now, but every star now has a declination and rate of ascension up in this sphere and those numbers locate where it is. So that's how astronomers have done what they've done with all of the stars, or many of them. And now I guess all of us know about the North Star, which is also called Polaris. The North Star is up there in the north, and in the Earth, the axis of the Earth that it points pretty much to the North Star. So as we rotate around that North Star stays in the same position. And if we were right here, we would always look right up in that same place for the North Star. Well, it turns out, that it is 433 light years away. Well, what does that mean? What is a light year? Well, let's talk about that. What is a light year? It is the distance that light travels in 1 year. Now, the light travels from the sun to the earth in 8 minutes. But how far will it travel in 1 year? Remember that it was 480 years is how far the North Star is. 480. So the light that you see there, the North Star, left the North Star 480 years ago. That's awesome. That's a long ways. Wow. Okay. That is a long ways away. Light travels at 186 miles a second. But how many seconds are there in a year? Well, there's 365 days in a year and 24 hours in a day. So you have 8,000 hours in a year. And then there's 60 minutes in an hour. So you have to multiply that by 60, you get the number of minutes in a year. And there's 60 minutes, 60 seconds in a minute. So you have 31 million seconds in a year. But light travels at 186,000 miles in a second. So if that times that is how far, that's how many miles. Now note that's millions, thousands, millions, billions, trillions a month. But notice that there's 3, 6, 9, 12. They put the 5.88. Mathematicians use 10 to the 12th. It's because it's 12 up over there. They don't have to bother with all those zeros then. So the mathematicians like to make things easy. So, but that's just 1 light year, that many miles away. North Star is 488 times that. Awesome to me. I'm in awe when I think about that stuff. Yeah, how far away is the nearest star? Well, it turns out it is 4.3, about that, 4.3 light years away, which is pretty close. That's our nearest one. It takes the light from the nearest one took 4.3 years to get here. It is Alpha Centauri. Okay, and it is the 3rd brightest in the sky. Okay. Here are some other bright stars: Sirius, Rigo, Betelgeuse, Arcturus, Vega. These are other bright ones. I'll talk a little bit more about them. Okay, Betelgeuse and Rigo are in the constellation Orion. Have all of you seen the constellation Orion? And okay, and Sirius is the brightest star in besides our sun, the brightest one in the sky, and it is somewhat near. It's a little bit below and to the left of Orion. Here is a little drawing of Orion. Here, the 3 stars in the belt really you pick it out pretty easy. But this one right here is Betelgeuse, and this one is Rigo. These 2 up in here are not quite so bright, but these 2 are very bright. Here. Okay. Now the question is, how do they know that Alpha Centauri is 4.3 light years away, and the North Star is 488 light years away? Well, the astronomers have developed various methods of measuring this distance, and some of them are rather new with the new equipment that they're able to have, but there's 2 of them that have been around for many 100 years or more. Okay, and okay, they found out different ways of measuring the distance. And there are 2 ways: the parallax method and seated variables. Okay, the parallax method. Here, the sun is right here, and the Earth orbits around. Okay, and there's a star out here, and they want to know how far away it is. Well, as we are moving along, right when they get right there, they look out at that star, and they take a picture of it. of that star. Well, there are stars behind it, way out, way out. And this star is in the picture with those other stars. They aren't instant gratification. I mean, they're willing to wait. So they wait until it comes around and they get right here. And they look out again at that star, take a picture, and they realize that that star, with respect to the other stars that really are so far out, don't move, it moves depending upon whether you're here or here. And they are able to measure that angle. How the astronomers do that exactly, I don't know, but it's amazing to me. Okay, so what is some more mathematics? In high school, while you learned about the tangent of that angle right there, alpha. Tangent of alpha is R over D. This is R, a radius here, and D is there. So if you know that R, which is 93 million, right here, and if you can measure alpha, you can get D here. Amazing. All you have to do is measure alpha, and they do it. Well, here's the distance to the star. And here's the 92. Instead of 93, astronomers use the 92.9, and they multiply it by 360. Oh, and divided here is 2 pi. Now, a pi seems to come in with the mathematicians all of the time, but anyway, it's there. And then this number right here is the angle that they measure. Okay? And when you put all of it, they measure that angle, and when we put it all together, they come up with Alpha Centauri is 26 times 10 to the 12 miles, and the distance in light years is 4.4. Now notice that this is 748 and this is 326. Now the 326 comes from this and the 186,000 miles per second. And if you figure it all out, why you come out with the 3.26 and 4.3 light years, something like this, for how far away Alpha Centauri is. But just by measuring this angle. I want to say something about this angle right here. Oh, if that number is 1 instead of 0.748, if it were 1, this would be 19 right here. This would be 19 times 10 to the 12 miles. Okay, and that one is what they call an arc second. And how big is an arc second? Obviously the angle is pretty small, but think about it. If you go up, about halfway, you're at 45 degrees. Okay, you come down here, you're about 5 degrees. And you go to down here, 1 degree. But now, if you divide that 1 degree up into minutes, you have 1/60th of a degree. And if you divided that minute up into 60, you have there are 60 seconds in every minute, and in a arc second, it's 1/10 of that. And that's where this 360. So this is 1 arc second. They measure. Can you imagine how small an angle that is? I don't, how the astronomers are able to measure it, I don't know, but they can do it from the photographs. And they measure that thing and they come up with how far it is. 4.4 light years. Now here's some chicken scratch that I've done to figure out these numbers. And there's more chicken scratch. And more chicken scratch yet. But notice down in here, I finally come up with 26 and 4.4 down in here. So that's that's my mathematics. my astronomy book didn't tell me. They told me about arc seconds. I didn't know what an arc second was, and they told me about 3.26. They gave me that number. Where did that number come from? Well, I had to figure it out. So anyway, that was the parallax method of getting the distance to the stars. There is also Cepheid variables. Now, Cepheid variables are particular types of stars that pulsate. They pulsate in brightness at a regular period. They look at one star and they say, "Oh, look at that! It goes every 2 days. It goes up like this and back every 2 days. Wow, that's interesting. Oh, and this one over here, every 10 days, and so on." They look at them, and it is regular. Well, this woman, Henrietta Swan Leavitt, is the one that is responsible for discovering this. She is a woman astronomer, and she discovered the relationship between this luminosity of the star and its period of pulsating. And she did this in 1909. And she did it looking at, according to the records, thousands of stars she looked at and looked at the photographs of them and finally came to this conclusion and wrote a paper on it. She went to Radcliffe, which is a college with a women's college at Harvard, and she worked with the photographs. She was not allowed to work with the telescopes because women were not allowed to at that time to use the telescope. Only men. Oh, wow. This was in 1909. That's way back. It's amazing. Anyway, eventually the astronomers realized that she was important, and they named an asteroid after her and a crater on the moon after her. Good. So, and down here, notice this is working. Yeah, period and days of the luminosity. 1, 10, 30, and over here is the absolute magnitude of its luminosity. How bright it is, and she came up with this curve here. So this was an amazing find. So from this, you look at the visual magnitude of a star. You look at it, you say, "Oh, it's so bright." That's this little m. The astronomers have all of the stars. They look at it and they determine how bright it is, and they assign the brightness by m. And it turns out that the period of these are the seated variables. It is a period of it illuminating, and from that they get the absolute magnitude from that graph you saw before, and that's m. Okay, and put the m and the m into this formula, and you come up with the distance to the star. Now, somewhere or another, the astronomers have figured out this equation. We don't have to worry about it, but that's how they do it. How they did it before they had more different ways nowadays to figure distances. But that was always it's very interesting to me. And here are a bunch of stars. Of course, our sun is one of them. There is, by the way, this is the brightest, the next brightest, and so forth, going down this way. Sirius, Alpha Centauri, Arcturus, Vega, Rigel, Betelgeuse, and visual magnitude. You look up at that and you see how bright they are. Well, for some reason or another, the sun is a minus 26. Now, why they have minus as being the brightest, And then as it gets less bright and it finally goes from negative to positive, why the astronomers did that, but we don't have to worry about it. That's what they do. And that's not our concern with this. But the absolute magnitude is sort of the same way here. No, now, the absolute is really how bright it is. You know, if a star is a long ways away, it wouldn't be so bright. But if it were closer, it would get brighter and brighter. Well, it turns out that the absolute magnitude, the brightness, this M, the big M, is the astronomers have figured out that if the star were 33 light years away, it would be this bright. They would be this bright. It's the same type of thing here. Now notice that here our sun is 4, so it's way down in here, you wouldn't hardly see it. If it were 33 light years away, our sun. But Sirius now is brighter. And Alpha Centauri is not so bright, but here, look at Arcturus is a minus. So that's up in here. It's fairly, well, Arcturus is about, well, look at how far away it is. See, it's close to the 33. That's why Arcturus this and that is pretty close to the same. And then notice these two, -6 and -7. Can you imagine how bright those are being 33 million miles away and they're still that bright? They are huge stars, both of them, Regal and Buto. And look at how far away they are. Those two stars are a long, long ways away. And they're still pretty bright for us in Orion. So that's enough about that. Here is a graph of our sun, how bright it is, and the other ones are this is negative numbers, and this is negative, and then a positive Betelgeuse down in here. See, okay. And here is the absolute magnitude. Our sun is way down in here, hardly bright at all. Okay, but here is Regal and Betelgeuse. Look at how bright they are. They're really bright. Well, oh, here is the distance in light years, and of course, if the sun is 0, it's right here, and these are pretty close compared to these two. All of these are pretty close, but because they are so huge, they're still bright. So, let's see. Okay, here is, these stars. Sirius, you see it in the winter time now, and you can see it now. Alpha Centauri, you can't see it on Cape Cod, it's in the southern hemisphere. If you're in the southern hemisphere, in Australia, you'd be able to see, Alpha Centauri, but you can't see it from here. And Arcturus and Vega, you see in the summertime, and Regal and Betelgeuse in the winter now, right now. So I think to me, I am awestricken by these things. The more I look at them, the more I'm just amazed at it all. I look in awe. So, okay, are there any questions? Huh? No, yes,
How far away is the furthest star that we can see?
a louder,
How far away is like of the stars we see, which star is the furthest away?
oh, that we see?
Yeah, that
Oh,
we can see with the naked eye, that we see with the
It's
naked eye.
something around, I think it is 6. In the little lamb visual, and if it's less than 6. No, if it's more than 6. Then you can't see it. Okay, so 6 you can just barely see with the naked eye.
And how far away
Okay,
is that?
and I don't know.
Okay.
I've seen it, but I don't remember. I think yeah, I think it could be a couple of thousand light years away. I think another talk or another thing that I would like to study, find out about, is the Milky Way galaxy that we're in. Where are we, and where are Regal and Betelgeuse and the other stars with respect to the galaxy? You know, the galaxy is a few thousand miles, a few thousand light years in diameter. I don't think it's millions. I think it's thousands. But I would like to study that more and maybe talk about that. Because that would be awesome also. Okay, well, I think, by the way, we have some cupcakes back there.